Welcome everybody to Cross-Classified Models Part 2, Model Fitting. My name is Professor George Leckie. So I'm taking over from Bill, who did Part 1. And in that first lecture, he introduced cross-classified models and the practical example, which was the Fife dataset, the Scottish data on students in secondary schools and their primary school histories that they've been to and how they performed in their end of school exams. So we're going to start fitting some models to these data, but before we do that, we need to show you some model equations. And so I'm going to introduce some notation and classification diagrams and so on. We'll then work our way through a series of cross-classified models, very basic, just to get a flavor of these models. We'll show you some of the consequences of ignoring cross-classification, and we'll look at ways of describing the kind of complex clustering, residual clustering that there is in these models, these so-called variance petition coefficients and intraclass correlation coefficients. We'll add explanatory variables to the model and see how we can assess what's going on in different parts of the model, and that will lead us in nicely to the follow-on video, which will be back to Bill, where he'll look at some other applications beyond education of these cross-classified models. So that's our battle plan. Let's go. So a recap of these data. The data set is from Fife in Scotland. It was used in a very early paper on cross-classified models, which actually used maximum likelihood estimation. We are going to be using MCMC, Markov chain Monte Carlo methods, to fit the models in this lecture, as they're much more capable as data sets get bigger or as models get more complex. And so that's a fairly standard approach for fitting these models. So let me get my pen out. What have we got here? We've got some 3,400 students. They're nested within just 19 secondary schools, so not a huge number of secondary schools. Primary schools are much smaller, and these kids had previously attended some 150 primary schools. The outcome is the end of secondary schooling exam score, so the kids are age 16. It's a total exam score across different subjects, and it ranges from 1 to 10. With 10 being the highest performance. We've got lots of explanatory variables to play with. We've got things like dummy variable flags for whether mothers and fathers stayed in education beyond compulsory schooling themselves. We've got some earlier test score on verbal reasoning for our students when they entered their secondary schools at age 11. We've got some kind of measure of whether the secondary school which they're attending is their first, second, third, fourth choice, okay, as well. We have a measure of the social class of the family, and we've got a flag for whether the students are boys or girls. So all of these could explain, of course, why some kids score higher in their end of school exams than others. But they can also explain why some secondary schools appear to be performing higher than others, and also why some primary schools might appear to be higher scoring than others. So we're interested in putting those variables into the model to get more understanding. So let's look at the very simplest cross-classified model that we could fit to these data. It's very simple because it's going to include no explanatory variables initially. So what's the point? Well, the point is we're trying to quantify the degree of secondary school clustering and simultaneously the degree of primary school clustering in our outcome variable, the attainment score for child I, and I have these 3,000 kids. So the model has only really got an intercept in it to estimate the overall average performance at age 16, but we have these school random effects, primary school random effects, and student residuals. And so we've got this breakdown of variability. And these random effects and residuals, we have standard multi-level assumptions that the school effects are normally distributed, the primary school effects are normally distributed, and the student residuals are normally distributed. And in each case, they're normally distributed around means of 0. These are relative effects. And we estimate, crucially, the variance of the random effects at each level. Okay, so we have the school variance, that is the secondary school variance, the primary school variance, and the student variance. And so what we're really doing here is we're estimating an overall mean, beta 0, for your attainment at age 16, but we're doing a decomposition of the variance in attainment scores into separate components of variance associated with different levels of analysis: the secondary school level of analysis, the primary school level of analysis, and what's left over, and what happens within schools, essentially. And we want to know, well, where does the variability lie? That's our starting point always for doing multi-level models. Now, if you're watching this video, then you'll know something about two-level models already, because that's the kind of prerequisite topic, and even three-level models. And you'll be familiar with kind of IJK notation. Now, you'll notice here in the equations I'm showing you, I'm not showing you the attainment score for child I in primary school J, in secondary school K, because this IJK notation is what we call hierarchical notation. It implies a hierarchy that students are nested within primary schools and primary schools are nested within secondary schools. Now, we know that's not the case from Bill's part 1 video, because we saw that each secondary school draws its students from many primary schools, but each primary school simultaneously sends its kids to multiple secondary schools, breaking down a naive 3-level hierarchy. So that's why we're doing cross-classified models. But because we can't do a hierarchical model, we can't use the usual hierarchical notation either. And so rather than IJK notation, we're going to use something called classification notation, which is what is being used on this slide here in terms of the equations, and that's why things look a little bit different. But I'll explain the notation in the next slide. Essentially, both primary schools and secondary schools are conceptually at level 2 in the hierarchy. So in this classification notation, the only index we've got, in a sense, is I, which is going to uniquely identify all 3,400 kids in the data. Okay, and then we have those random effects, the U's in the model, and we have these kind of 2 and 3 superscripts on the random effects, and actually you can see them down here as well. There's a 3 superscript and a 2 superscript. Now, this is just to distinguish between different sets of random effects, different high-level classifications. In our case, the 3 denotes the secondary school random effect, and the 2 denotes the primary school random effect. Now, the subscripts on those random effects, particularly if you look at the previous slide, is SID and PID. It stands for secondary school ID and primary school ID, and these are what we call classification functions. And essentially, in parentheses, we have I, the index for the student. Now, if you plug in the unique ID for a given student, what this function does is it spits out the secondary school that kid attends, or the primary school that kid attends, if we're using the PID function. So if, for example, student 1 in our data set attends secondary school 5, and previously attended primary school 17, then the way these functions would work is if we plugged in a value of 1 for the student identifier, the function, the classification function SID of I would spit out 5, telling us that that kid attended secondary school 5. And likewise, the PID of student 1 is the primary school student 1, which is primary school 17. And all of this will then kind of feed into the model equation. And so the model equation for student 1 is the attainment score for student 1 is equal to the overall average score across all 3,000 kids, plus a secondary school random effect. And SID of 1 is 5. And so we now just have a 5 as a subscript, telling us that that's the secondary school random effect for school 5, whereas they attended previously primary school 17. And so this U sub 17 superscript 2 is the primary school effect of primary school 17. And then that's not going to perfectly predict the student's age 16 score. We're going to be left over with the student residual for that particular student, and that's the EI. So that's just how the notation works. It's still a kind of multi-level model with different sets of random effects, but because we don't have a strict hierarchy, we have to use a different notation. And this notation is quite popular in the statistical literature. And if you're reading journal articles, you'll certainly see it. And so that's why we've gone through it in a bit of detail here. Okay, so classification notation is very flexible, and if you had not just a two-way cross-classified model, but a three-way cross-classified model, because maybe you're bringing in the neighborhood of residents in there as well, or maybe even bringing in school districts and regions, you can have all this kind of complexity brought in. So this notation is very scalable, which is great. A limitation is that the notation in itself, what we saw on the previous slide with the equations, doesn't really give you a sense of what the data structure looks like. And so we like to complement the equations on the previous slide with a so-called classification diagram. And for this model, it's very simple, and it's done like this. The lowest level is student, and so the outcome is always measured at the lowest level of the model. And student scores are nested within secondary schools, and they are separately nested within primary schools. But the fact that there's no arrow between primary and secondary school means that there's no kind of strict nesting of one within the other. They are said to be cross-classified. And so this kind of classification diagram communicates the structure. We can tag on additional boxes, which are often called nodes, and additional arrows to indicate what's going on. And you might want to compare that back to the unit diagrams that Bill showed you in part 1. So often researchers will include these diagrams in their papers as well. Let's have a little bit more understanding. Let's consider student 1. Let's pretend that I'm the proud father of student 1, who's an excellent student. And this is the equation written out for my child 1. They attended secondary school 5 and primary school 17. And these U's are the effects of those schools. So here is my child, and on the y-axis we have the attainment, and you can see my child is right at the very top there. That child's doing fantastically. So how does this model work? Well, models always work in the same way, in the sense we start off at 0, okay, an outcome of 0, and then we tag on the estimated intercept, beta 0. Okay, so this thick black line is giving you the overall average score on the data across all 3,400 children, if you like. Now, my child's up here, and they go to a particular combination of secondary and primary schools, secondary school 5 and primary school 17. And this line up here is, if you like, the predicted mean score for the subset of kids like my own, who first went to primary school 17, and then went to secondary school 5. But how do we get to that point? Well, let's go back to the overall average line, beta 0, and let's just consider kids who attend primary school 17. Okay, those kids in general were scoring above the overall average for whatever reason, maybe a combination of selection into schools, maybe it's in a relatively prosperous neighborhood, but also combined with perhaps that primary school is truly effective. So that dotted line there, which I've highlighted, is showing you the mean performance of kids in primary school 17. What about from the other perspective? Let's just consider all the kids in secondary school 5. Okay, well, they are on average performing like this, okay, which is this much better than the overall average. Okay, so here you can see the secondary school effect taking us up to the higher of the two dashed lines. But my kid has attended both these schools. First, they attended primary school 17 and they got that effect. Then they attended secondary school 5 and got that effect. And if we add those two effects together, that is how we get up to this higher solid line up here, which is giving you the predicted performance of kids in that particular combination of primary secondary. So these are modeled as additive effects. You can see that here. We're simply adding the primary school and secondary school effects together. There's no interaction. That is an extension that one can do in cross-classified models, but we won't discuss it here. Now, having got to the subset of kids in the combination of primary 17 and secondary 5, we see we have 1, 2, 3, 4, 5 kids orbiting around that mean performance. Some with below with negative student residuals, some above with positive student residuals, and I am that delighted parent whose kid is somehow magically doing the best amongst all 5 of those kids there. and there you can see the residual EI. So hopefully you can see mechanically how the model's working, how it's decomposing the variability in attainment into kind of mean performances associated with primary school attended or secondary school attended, and then residual variability attributable to a given student. Okay, let's think a little bit more about the data structure and some implications for our results. We almost know some of the things that we're going to see in when we come to fit the models just by having an understanding of the dimensions of the data. And in particular, we have only 19 secondary schools. So my between secondary school variance is not going to be estimated very precisely because it's kind of the variance of 19 means. Well, 19 is a small data set, right? So I'm going to have a big old standard error on my between secondary school variance. Okay. But on any given secondary school, we have lots of students. And indeed, on average, we have 181 students in each secondary school, which means I can get a relatively precise estimate of the specific effect of, for example, secondary school 5, my kid's secondary school. So we get relatively precise estimates of those guys. But at the primary level, this kind of story flips around because here we now have lots of schools, some 150. And so my between primary school variance, sigma u squared sub 2, that will be estimated relatively precisely with a relatively small standard error because I've got a big sample of 148. But in contrast, for any given primary school, let's say primary school 17, the one that my child went to, on average, we've only got 23 students per primary school, which is a much smaller sample size. And so we're going to get bigger confidence intervals, less precise estimates of individual school effects at the primary level, just because there's less data. So it's quite good to kind of have a sense of your data structure because it's kind of telling you what you're going to see and giving you understanding once you do see the results shortly. So let's fit our first models. So as I indicated already, we're fitting all models by Markov chain Monte Carlo methods. But we are doing so using kind of sensible starting values in the MON software. Our priors that we're using are minimally informative. And so the results are effectively the kind of same results that you'd really get from a maximum likelihood estimation. But MCMC is much more scalable to bigger data sets, more complex models. So it's quite good to use. So the model which I've shown you so far is actually model 2. That cross-classified model with no explanatory variables, but with the secondary school random effects and variance and the primary school random effects and variance. So we estimate the variance of these parameters of these effects directly, and that is what is being summarized here. Now we actually have an even simpler model, model 1, where we do not include the secondary school variance or the primary school variance, because in this simple model we have deliberately excluded the secondary school random effects entirely and the primary school random effects entirely. Why? Well, the contrast of model 1 to model 2 provides us with a test of whether we have any clustering in general, because model 1 ignores the clustering, model 2 takes it into account. So a difference in results between those two models is giving evidence that there is clustering. And by difference, I mean the fit statistic. So we're fitting the model by MCMC, and so we have the Bayesian DIC, Deviant Information Criterion. It's a bit like the AIC or the BIC if you fit models by maximum likelihood. And so just with those statistics, we like smaller values. And so as you fit more complex models, the DIC drops, and you want it to drop by at least 2 to 5 points, really. But any drop of that magnitude or bigger is suggesting that the more complex model is statistically preferred. So we've got a whopping drop of some 383 points when we account for secondary school clustering or effects and primary school clustering or effects. And that is telling us that we have meaningful variation at those higher levels. And indeed, as we'll see shortly, if we add up these variance components, we'll get an estimate of the total variance, which will actually be pretty similar to the 9.363 variance we had in the first model. And what we'll see is that those two higher levels, secondary schools and primary schools, are accounting for about 16% of the overall variance in the attainment. And so in a cross-sectional, cluster cross-sectional setting such as this, that's pretty meaningful and in line with the literature on school effects. We have clustering, it's substantial and it's statistically significant. We should proceed with the cross-classified multi-level model. Here we go. Next slide here. So model 2 is just a model we had already. We might at this point go, well, okay, so we've established that there is this kind of clustering in general attributable to secondary schools and primary schools. But what we should really check is whether maybe it's just one or other of those sources of variation which is dominating. So can we get away with a simpler model which only accounts for, let's say, the secondary school clustering and ignores the primary school clustering? Because if we could, that would be a two-level model, and we could get away with models that we've already learned. We wouldn't have to learn these fancy new cross-classified models. So we should always justify to our audience that the full complexity of the model we're presenting is required. So here I compare model 2, the full cross-classified model, to model 3, a simpler model which ignores the primary school effects. It sets them all to 0, and therefore the primary school variance to 0 effectively. So what happens when we do that is that the DIC, which the smaller the better, now gets bigger, okay, and now increases by 262 points. So that's telling us that model 3 is a statistically worse fit of the data than model 2. We should stick with our cross-classified model, not go to the simpler two-level model. And what it's really telling us is that over and above acknowledging the different secondary schools that students go to, there's still meaningful variation between primary schools. So students who attend the same primary school are significantly more alike, have more similar, more highly correlated attainment scores than students from different primary schools. And that is not simply because they went on to experience a common secondary school. That's the kind of substantive story there. So that's telling us that we can't shift to a simpler students within secondary schools model. Well, how about this? Can we instead shift to a simpler students within primary schools model? Okay, so model 4 is going to this time knock out the secondary school effects to see whether we can get away with that. So it's a bit like setting all the secondary school effects, all the U's to 0, and therefore the secondary school variance is 0. What happens? Well, once again, the DIC or the cross-classified model then goes up by more than that 2 to 5 points. It actually goes up by some 30 points. So statistically, model 4 is a worse model than model 2. Okay, so the more complex model is statistically preferred. And so we've really justified now that we need a cross-classified approach. We have two sources of important clustering going on. Clustering in students age 16 scores due to common secondary schools attended, and clustering in students age 16 scores because of this history of earlier primary schools attended. So students from the same secondaries are significantly more alike than students from different secondaries, and that is not simply because of shared primary school experiences. There's something over and above that associated with secondary schools is the story. Okay, next up, we've got variance petition coefficients and intraclass correlation coefficients. So these are these kind of great statistics in multi-level modeling, which you get to quantify the degree of residual clustering you have. On the previous slides, we've established we have statistically significant clustering, but what we haven't done is additionally communicate whether that is also of practical significance. Okay, so the clustering's got to be not just statistically significant, because in a large data set everything is statistically significant, but the clustering has to also be meaningful, correlations between kids within the same context. These are very easy to calculate. So The secondary school VPC is the proportion of overall variance in attainment, the sum of the three variances, which is attributable to secondary schools. So we divide the secondary school variance by the summation of all three variances, and we get out a proportion which is 0.043. And we say that 4.3% of the variation in age 16 scores lies between secondary schools. Now, expressed as an intraclass correlation, what we're saying is that the correlation between two kids who share the same secondary school but attended different primary schools is 0.043. So a small positive correlation. There's some kind of similarity, due perhaps to true, genuine differences in quality of education between secondary schools, but also clearly due to selection effects into secondary schools. Now, at the primary level, we just do the same thing, but this time we divide the primary school variance by the summation of all three variances, and that gives us out a larger 0.119. So some 11.9% of the variation in age 16 scores lies between primary schools. There's stronger clustering attributed to primary schools than there is secondary schools. And so the correlation between two kids in the same primary school, but who went on to attend two different secondary schools, is 0.119. Now, our highest VPC and ICC relates to when we're saying, well, how much of the variation is attributable to schools in general, both primary schools and secondary schools combined, if you like. So we put both those variance components on the numerator, divide by the summation of all three on the denominator. That gives us 0.162. So 16.2% of the variation in test scores at age 16 is attributable to the two sources of clustering combined or considered simultaneously. And as a correlation, we're saying the correlation between two kids who attend not only the same primary school, but then went on to the same secondary school is 0.162. So in the literature, these would be considered of practical importance, and they're in line with other studies. And so not only do we have statistically significant clustering, but it's also meaningful in this literature, these magnitudes. Right, this brings us on to our next model, where we are going to introduce covariates. And all the covariates that I'm going to introduce are actually characteristics of the students, not characteristics of the secondary schools or primary schools, although those can be introduced and would often be introduced in the next model. But in our data, all we've got here are these student characteristics to play with. We have a measure of their attainment at age 11 when they entered their secondary schools, verbal reasoning test. We have a measure of their social class. Higher values indicate kids from more affluent backgrounds. We have dummy variable indicators of whether the father and mother stayed in school themselves beyond beyond age 16, essentially. And we have this measure of whether the secondary school attended was the first, second, third, or fourth choice for the child as well. Putting those explanatory variables into the model, we're going to explain the variation in the outcome. And so we expect the residual variances to go down at all levels. Why at all levels? Because kids aren't randomly assigned to schools. There's going to be kind of social class clustering in different schools. And so if you adjust for social class, we're going to explain part of the variability between secondary schools. And so if we do so, then the magnitude of the secondary school effects will in general reduce towards zero. Likewise, the primary school variance will go down and their effects will get smaller in absolute magnitude. And even within secondary schools and primary schools, some kids perform better than others, and that's related to these characteristics. And so residual variance will go down as well. So I probably expect to see a positive coefficient on verbal reasoning. Kids that are doing better at age 11 carry on doing better at age 16. Positive relationship between social class and attainment, I expect to see. Kids from more affluent backgrounds go on to score better at age 16, all else equal. Likewise, kids whose fathers stayed in education themselves or mothers stayed in education themselves will likely score higher at age 16. And the only negative coefficient is likely to be on choice. If you don't get, if the school you're attending is not your first choice, but your second or your third or your fourth, it's less and less a school you wanted to go to, and perhaps that might be actually negatively associated with how you go on to perform. We shall see. Here we go. Here are the results. And so model 5 is the new model. It's a cross-classified model extended to include this set of covariates we've just gone through. And indeed, all the coefficients are positive and statistically significant, apart from the hypothesized choice variable, which was negative and significant. I can judge significance in normal ways. Divide point estimates by standard errors. Is the ratio effectively 2 or higher? And of course, you can translate these into p-values or calculate confidence intervals in the normal way as well. But we can see very easily they are all significant. Now, from a multi-level perspective, as well as being interested in the regression coefficients, we're very interested in the variance components and the proportion of variance that we explain at different levels of analysis, essentially R-squareds at the secondary school level, the primary school level, and at the student level. And so we can calculate things like the proportion reduction in a variance component, and we see the secondary school variance drops massively, and indeed it goes down to some 97%. So actually, these 5 predictors explain away nearly all the variability between secondary schools, which is quite an interesting finding. We also have very powerful explanatory power at the primary school level. That variance also drops massively as well, it drops by some 82%. And then even within primary secondary school combinations, the residual variance, which is pretty large, accounting for 84% of the variance in total, well, that effectively halves as well on the inclusion of covariates. So we've got big explanatory power associated with these covariates, but especially at the secondary school level and primary school level. So those wide educational disparities that we saw between both types of schools are kind of pretty much wiped out when you take into account these background characteristics of kids, suggesting rather strangely perhaps that the schools don't appear to have particularly differential effects from one another once you've ruled out the kind of selection into schools, which is clearly a big feature of the Fife data. It's very sensible to always do residual diagnostics after any statistical model, including multi-level models. Now, in our cross-classified model, we're particularly interested in higher level effects. And so this is a so-called quantile plot of the secondary school predicted effects. And so we've got the predicted effects essentially on the y-axis that have been standardized against so-called normal scores on the x-axis. And the reason we do this plot is that we've made a normality assumption about the secondary school effects. And so you want these effects to lie on a kind of 45-degree line. And what we see is that they're pretty good in the big scheme of things. There's only 19 of them. We do the same at the primary school level. These, again, there's some kind of curvature rather than a straight line relationship, but in the big scheme of things, most researchers will be happy that that looks approximately normally distributed. Now, if you've not seen quantile plots before, just do histograms and then check that the histogram of predicted school effects looks like a bell curve. You could even superimpose on a normal curve. Okay, that's fine to do that. So the plots on the left are kind of for residual diagnostics, checking model assumptions. Normality assumptions are pretty good. Plots on the right are actually more for substantive interpretation. So having adjusted kind of quite richly for the different types of kids who go to different schools, including a measure of prior attainment, these residualized secondary school effects and residualized primary school effects lie much closer to being perhaps measures of the actual quality of education imparted by secondary schools and primary schools. And so that's what these scatter plots are kind of showing. On the y-axis, we've got the predicted secondary school effects here and the predicted primary school effects down here. In each case, we rank schools in rank order from the least effective school, secondary school in this case, to the most, and the least effective primary school to the most effective primary school. But we've got big old wide 95% confidence intervals around these effects. and they'll be in a sense wider for the primary schools. Note these are on different scales. Okay, these plots, they're not directly comparable, but they'll be wider for the primary schools because in general there's fewer kids per primary school than there are for secondary school. But in terms of statistical separation, because the primary school variance is much bigger than the secondary school variance, and we've got many more primary schools as well, we've got some statistical separation. So for primary schools at least, there's a little kind of subset of primary schools which appear to be significantly less effective than the Fife average given by the zero line, and another subset up here who would be judged to be significantly more effective provision of education. But the majority can't be statistically separated out from the overall average or one another. Secondary school have only got 19, their variance is smaller, and it turns out really none of those schools can be statistically separated from one another or the overall average. And remember, once we adjusted for all the covariates, that secondary school variance is pretty tiny. And so that's what's being depicted there. One thing which you might notice is that this school down here is perhaps a bit outlying, and indeed it's down here as well. It's school 19. Okay, so these residual diagnostics do hint that one school appears to be kind of substantially different perhaps from the rest. So there's very little variability between secondary schools, and a fair bit of that is attributable perhaps just to one school, school 19, differing from the rest. So that brings us on nicely to our very last model, where we enter in a dummy variable for being in school 19, because it's an outlier. And so rather than just dropping the school, we're actually going to build in that departure from normality, if you like, into the model. Simultaneously, and we could do this in 2 steps if we want, but simultaneously, we've actually dropped the secondary school random effects. If you left them in, they'd get even smaller and effectively 0, and so that's why we're taking them out. So we're kind of interested in whether this model is preferred to the previous one. This one perhaps got a better characterization of secondary schools as really just being one cluster, schools 1 to 18, performing relatively homogeneously, and then one other school, school 19, which is performing significantly worse from that kind of cluster. And so that's what we're doing here, rather than allowing every school to have its unique effect. So let's just see what we get back from this final model. And it should be noted before I do that, but because I don't include the secondary school random effects for the other schools, this model just drops to a 2-level model with students at level 1 nested within primary schools at level 2. And so we could fit this as a regular 2-level model. But let's see whether it's preferred. So here we go, last set of results. Model 5 is the previous model, which included the secondary school variance. And you can see there's a very small variance, very imprecisely estimated, hinting that we could probably get away with removing it. We did remove it in model 6, but instead we put in a dummy variable for that outline school, which seemed to be far less effective than the rest. And indeed, in contrast to schools 1 to 18, school 19 is scoring some 0.6 points less on average, kids in that school. And that's pretty sizable. You know, it's kind of pushing on to be 3 times the effect size of kids whose parents stayed in school, okay, or mothers there as well. So it's a pretty sizable effect when comparing to some of the other covariates. Crucially, we should check that model 6 is statistically preferred to model 5, as well as being a simpler, more parsimonious model. And it's pretty similar, really, because the DIC drops, okay, suggesting model 6 is preferred, but it only drops by some kind of 4 points, which is pretty borderline. So statistically, model 5 and model 6 are pretty comparable, okay. And so in reality, you could go with either of them, really, whatever kind of pleased you most in terms of the story you're trying to tell. They're kind of statistically comparable fits. So it's picking the one which makes more substantive sense would be how you would proceed. So just to end up, in this lecture, part 2, we've actually fitted cross-classified models to the Fife data. And To do so, we first had to introduce the model equations, and that required some new notation and diagrams because we couldn't use regular hierarchical notation because we don't have a hierarchy. But we could use concepts such as measures of residual clustering, the ICC and VPC that apply in simpler models, and we've adapted those to the cross-classified setting to be able to detect, well, which source of variance is more important. It was primary schools rather than secondary. Of course, we could add in predictor variables, just like we normally do, to explain the variability of different levels of analysis. And interestingly, in this example, just those 5 student characteristics pretty much wiped out all of the secondary school variability and a lot of the primary school variability. And actually, that kind of led us ultimately to reject the cross-classified model once the covariates were included. And you could actually revert to a simpler model at that point. So that's often the case, actually. When you add explanatory variables in, the residual part of the model is going to change, and you could lead to a different structure than what you thought initially. So that's me done. I hope you found that interesting and enlightening. What follows after this video is the third and final video of this cross-classified series, and that will be Bill presenting some further applications of cross-classified models to some veterinary science examples, and he'll introduce some exciting new model extensions to the basic cross-classified models introduced here. So thank you very much for listening, and good luck with your learning.